Okay, so as Paul said, I'm going to take my atomistic results and now try to play around with them to actually see what we can predict based on that stuff. So I'm going to give a general introduction. Why is it interesting? Again, laser ceramics. I mentioned a bit this morning. I'm going to re-mention. Then I will show microstructural models that we've developed. Then I'm going to go into optical models. And I'm going to apply these two models to YAG ceramics, a tiny bit to alumina, and then try to actually see, can we predict what is the optimal ceramic for a maximum laser performance of these ND-YAG ceramics. So my favorite graph, again. So now I'm going to talk mostly in the mesoscale simulation area, so I'm going to consider grains. I don't really consider atoms that much anymore. Single crystalline ND-YAG lasers have been around for quite a while. They work very well, but you have to grow the crystal from the melt. Then you have to machine it. So it is very slow, it is quite expensive, and surprisingly, these have not that good optical properties because there's a lot of defects in the crystals. However, if we sinter ceramics from powders, it is fast, very economic, and we can go near net shape if we use something like SPS. So we almost don't have to machine anymore. We have a good final piece. The ceramics, however, as I said this morning, need to have similar, hopefully better, optical and lasing properties. So what I show here is the atomistically derived data that we have. We have, on one hand, okay, I'm going to skip again surfaces completely because I want to look at ceramics, so it's more grain boundaries that are interesting to me. We have grain boundary energies for doped and the undoped case for all of these 21 boundaries I mentioned this morning. So we have a certain population of grain boundaries. In a real ceramic, there will be a huge population. What we try to do in the simulation is to calculate a certain number of them, which we think, since it covers from very low sigma to reasonably high sigma value boundaries, covers quite well the spectrum of grain boundaries that one would find in a ceramic. We then have the surface concentration and the depth of the enriched layer, and then derived of that is the coverage. So that's the fraction of neodymium that we actually have in this grain boundary layer. So we're going to take this data and we will try to build a microstructure model. What we want from our microstructure model is we put in a grain size and we want to get out the population of interfaces we have, the number of dopants which are actually segregated at the grain boundary, and then compare this with the number of dopants which are in the sample. Normally people tend to use spheres to approximate grains. Spheres are not all that good because they're not space filling. So what we decided to go with is a rhombic dodecahedron, which has the advantage of being space filling. And so we have this grain here. The radius of the sphere which encloses it would be 2a. So we say we have this thing which has a grain size of 2a. You can then calculate its volume and the surface area by quite simple equations. And we say that, okay, the surface area of this grain is somehow going to be made up of the interfaces that we calculated. And we say the proportion with one an interface appears with is proportional to its inverse interfacial energy. So that's like the classical Wolf construction known for the equilibrium shape of powders. And we just remove the geometric constraint and we say, okay, the surfaces appear and it's proportional to the inverse interfacial energy. I have to say that the model makes no assumption whatsoever on how these surfaces are. So it's not that I say this is a 110 plane, this is a 111 plane. I just say somehow the surface area is covered. We can understand this to some extent. We can interpret as grain boundary faceting. So normally grain boundaries, when they are not in a low energy plane, are made out of little facets of lower energy planes. The total system will then have a lower interfacial energy. So how do we select the interfaces? Because we have what we've seen this morning, I can do multiple terminations for one interface. So I can basically, what that means is I can slice my crystal at different depths along the same plane. And I can just, if we etch them, I have an atom that passes from one side of the plane to another, I have a termination. So I have multiple terminations for the same direction. In equilibrium, obviously, only the lowest energy one would appear. So I say, okay, in equilibrium, I have these 4 here, which will appear proportional to the inverse interfacial energy. So I do the interfacial area for one specific plane is a function of the total surface of my grain, and then I do the inverse interfacial energy and the sum over it just to weight this distribution. In the non-equilibrium, I consider that all of them would appear, again, proportional to the inverse of the interfacial energy, so the same equation. But this time, I just select every interface I ever calculated. Based on that, I can then calculate the total number of dopants. So I know when I have a specific grain, how many neodymium atoms I would have in that grain. So I know, okay, in the unit cell this much, then a grain of a certain size has this many yttrium ions. From there, I know with the doping rate, the number of neodymium ions I have inside a specific grain. I also know from the surface area and the surface concentration how many dopants will be sitting at the grain boundary. And from there, I can then calculate the effective doping rate, because I have dopants that move from the center towards the surface. So actually, the concentration in the center will decrease. And I can calculate this effective concentration based on the quantities we've seen here. If we plot this as a function of the grain size, and on this axis I have the percentage of dopants which are actually at the grain boundary for 1 atomic percent, 4 and 8 atomic percent, which are like quite good figures for what is done in an experiment. We can see that at very low grain sizes, in the nano range, we get like something like 20% of the dopants at the grain boundary. As we go up in the total dopant concentration, this gets less important. And also as we go up in grain size, we have less interface. Therefore, we have less dopants actually sitting at the interface. So this was the equilibrium model. So I had my 4 low energy interfaces. From this morning, we remember that the low energy interfaces do not accommodate a lot of dopants. So now let's look at the non-equilibrium model, where we can see that we have a lot higher proportion of dopants sitting at the grain boundary. So for very small grains and low dopant concentrations of 1%, we can get all dopants sitting at the grain boundary. And again, as we go up in grain size, this gets less important, and also as we go up in the total dopant concentration. So what does it mean for the number of dopants in the bulk? We have this curve here, which is the depletion of the bulk. That means we look at the red curve, and here for very low grain sizes, we can get something like 0.1. So we put in, that means we put in 1 atomic percent, we end up with 0.9 atomic percent actually sitting in the center of the grain. It is a bit more dramatic here, where for, let's say, at 500 nanometers, we also get this. So for reasonably large grains, we get quite a reduction in the number of dopants that are sitting in the center of the grain. So this means in a non-equilibrium case, we will have higher proportion of dopants that are segregated at the grain boundary. And as I mentioned before, for higher dopant rates, we can actually reduce this fraction of segregated dopants. What are the implications of this? We have, in this grain boundary region, we have very, very high fraction of neodymium ions, which are substituted for the yttrium ions. This is higher than 18 atomic percent. 18 atomic percent is really the lowest figure. It's not the mean value, it's the minimum. And the laser community has an effect they know is concentration quenching. And I have went into literature here. We can see that for certain, or for 3 different 1, 2, and 3 atomic percent neodymium, they get a reduction in this luminescence lifetime. Now, if this luminescence lifetime is reduced, we get less less of these stimulated emissions from what we saw this morning in the first talk. And so we get quite a significant loss, which will mean a loss in laser performance. This means that the neodymium that goes to the grain boundary is lost because it does not contribute to the lasing action. Okay, then we just put in more neodymium and we waste the one we put at the grain boundary. I don't think neodymium is cheap, but can't be that expensive. If this would be the only problem. However, if it segregates the grain boundary, it may locally affect the refractive index, which will lead to light scattering. We saw this with Carlos Pecharoman yesterday, that we have different refractive index layers in the material. It can change the transparency. And we have light scattering in this. Okay, so we would like to do some optical modeling to actually see this transparency as a function of grain size. The requirements for optical model would be, we would first of all like to make it generic, not only for YAG, we would like to do it for every type of ceramic. We would like to predict the optical transparency as a function of grain size, the porosity, the texture in the material, presence of second phases, and for my case, the segregated dopant layer. So first of all, what is the difference with light going through a single crystal versus a ceramic? In a single crystal, we have light coming in. A certain fraction gets reflected at the surface. Then the rest of the beam goes through. We have, again, reflection at this interface. And then the light gets transmitted. In a ceramic, we have much of the same thing happening. However, if we zoom in, we have the microstructure. We have grains, grain boundaries, pores, and surfaces, which all will somehow interact with the light going through. I will mention here that, okay, we can have the case where grain boundaries, we have a birefringent material. So we have one axis which has a different refractive index than the other. So we have two grains coming together. There will be a slight change of refractive index at the grain boundary. And therefore, we can have light scattering by this grain boundary. The other thing I will consider is the segregated layer, where we have basically the core of the particle, which has a different refractive index from the shell of the particle. There's a nice model around in the literature, been published by Appitz and Van Bruggen, and what they consider is the Beer-Lambert law to predict the real inline transmittance. So we have the intensity of the outgoing beam, the intensity of the incoming beam. There's something missing here, I spotted that this morning, too late to change. And we have a surface reflectance term, which will actually just reduce the amount of light going through. Then we have the sample thickness and the scattering coefficient. The surface reflectance term is quite easy. Carlos showed that yesterday. We would just do the perpendicular total Fresnel refractance coefficient, which is a function of the mean refractive index of the material. Then the scattering coefficient can be just the sum of a lot of different scattering effects that happen in the material, and I'm going to go into more detail here. For a birefringent material, what Appitz and Van Bruggen suggested is to construct this sort of matrix or particles in the matrix material, where we have a certain particles of a certain refractive index sitting in a matrix of a different refractive index. We can then work out what is the average refractive index change at the grain boundary, and we can predict this scattering coefficient as a function of the volume fraction, the volume density, and the scattering cross-section for a single particle. The scattering cross-section, we can obtain it using Mie theory, as shown yesterday, explained by Carlos, a lot better than I can ever do it. Or we can do it numerically using Rayleigh-Ganz-Debye approximation if we fulfill certain conditions. To include pore scattering, I had to go quite a bit back in literature. There's a very nice model from the 70s, it's older than me, where they used a log normal pore size distribution, which is given by this equation here. So you can see in a log plot we have a very nice normal distribution. And then we have the scattering coefficient for the pores, which is given by this equation here. Looks quite easy, but it's nasty to do in a computer because we have these improper integrals here. However, there are methods which one can find in numerical recipes, so we can integrate these numerically. The nice thing is, second phases, we can treat them exactly like pores. We just put in a different refractive index, and that's it. Okay, we implemented this into, again, yet another Java application. It is not yet publicly available, and I put the yet in square brackets because I have to find the time to polish it a bit. And then we may release it also on the website. If you ever get interested in doing this sort of simulation, maybe just send me an email and I will send you the latest, maybe not so stable version. Okay, so we just want to know, does this model actually work? The problem is, for YAG, we don't have any experimental data. So we tried to validate the model with respect to alumina. So we have the birefringent material, alumina. And this has been a master student actually working with Al2O3, Paul, and me. And he did a lot of SPS-centered samples. He measured the grain size. He measured the real inline transmittance, and we plot it here. And we can see if we plot the model curve, it really fits. So this model actually works. It is very simple, but it works. Okay, so we have a model which seems to work. Now, how can we modify it to model this segregated layer? The idea is to do coated particles. So now if you put a coated particle, so that's a particle where the center of the particle has a certain refractive index, the surrounding has another one, and then it's sitting again in the matrix with the same refractive index as the core. There is a publicly available code which does this. It's unhappily in Fortran, so we had to rework it a bit. But we can do just this setup. Okay, now how do we construct a microstructure in this case? Because we don't have the birefringent material anymore, we can do half and half, but we have to think differently. We could do it as a hexagonal close-packed array of spheres. However, the problem here is that the me theory considers isolated particles. So these guys will never actually touch, and we have a lot of isolated defects in the material, but we don't have the extended defect of a grain boundary. Another approach is to actually take the spheres, which have this grain boundary layer, and to embed them into a grain boundary-like matrix. And I also did the hexagonal close-packed case initially. But one can actually play with the volume fraction and get this, which is now way overestimated, can get this smaller and get it to the real volume fraction of the grain boundary. Next problem, what is the refractive index of doped YAG? And I did some calculations here based on empirical potentials. This is really, and I have to stress this, a first approximation. One should do this using quantum mechanical methods and not simple empirical potentials. But as a first approximation, we can consider this. What I did was I took my YAG unit cell and I gradually started filling it up with neodymium. And I calculated the refractive index as a function of the neodymium content. And so we can see that for the equilibrium case, on average, we're going to have about 0.1, which will give us a slight shift in the refractive index here. For the non-equilibrium case, we'll have a bit larger shift. So just remember this 1.59 as the refractive index of the grain boundary layer. So we calculate first for the non-interconnected model. So we have a lot of isolated defects in the material, and we can see that for different grain sizes, we don't change a lot because our refractive index will actually be here. So there's not a lot of change in the real inline transmittance as a function of the grain size. However, if you consider the interconnected model, things change quite dramatically. So we see, again, our, where is it, 5.9 should be, where is my scale so off, or am I looking wrongly? Okay, somewhere we're here. It doesn't matter all that much because the lines are quite flat. So if we have as a function of, for different grain sizes, so here we have the 10 micron grains, then the micron grain, the half micron, then we go down in the nanometer range. And we can see that for whatever refractive index this grain boundary has, we get a quite dramatic reduction in the real energy transmittance as our grains get bigger. So we can see that for 10 micron grains, it will be completely opaque. For the 1 micron grain, we get like something translucent, whereas for nano-sized grains, we get something which is transparent. So we see that one model predicts no reduction, the other model predicts reduction. Now, in reality, sadly, grain boundaries are interconnected, and this model will probably better describe the material. That means this predicts that grains should be small, and we should do nanoceramics to get the best transparency. So, put it all together, what is best? So we have these simulations of the microstructure, which predict this big grains, we get less concentration quenching, we get more active dopants, and we get more laser power. So we want to do big grains. They also predict that we sinter more towards equilibrium, we get less quenching, and we get more laser power. So we want to go as far to equilibrium as possible. This, however, tells us we want small grains, because then we get a higher optical transparency. There is a practical constraint because we cannot just dream up microstructures, but we got to actually sinter them. And that means the more we go towards equilibrium, the bigger our grains will be. And that means that there has to be an optimal grain size somewhere. Because on one hand, we get the reduction in transparency as we go up in grain size, which should follow a law similar to this. And we have a reduction in laser power as we go down in grain size. This means that somewhere there must be an optimal grain size. So to conclude, we can say that we can use atomistically derived data in larger scale models to actually predict quenching and transparency properties, in this case for YAG. The result tells us that we want grain as big as possible to have a minimum concentration quenching, get the maximum laser power. And we want to sinter as close to equilibrium as possible to get the maximum laser power as well. But we want grain as small as possible, which means, okay, we have a trade-off somehow, and we have to find the optimal grain size. This helps us to actually, I cannot give an exact number, this is the perfect grain size. However, this is really important, this work, because it helps us to understand what's actually happening in this material. It's not that as we go down in grain size, we get more and more powerful lasers, but we have another effect which people were not really aware of. So we have to find this optimal grain size, and now we understand what's going on in the material. That means we do less experiments, and we hopefully get to better ceramics faster. And with that, I thank you for your attention. I can answer questions.